Okay, so what we will do today is multidimensional scaling. And this is an application in big data. The goal is you have pairwise distances between sample points, and the goal is to find coordinates of those samples, or retrieve the samples themselves or similar samples. And where is this multidimensional scaling used? It's used in data visualization. And it's also used in dimension reduction, as you shall shortly see. Okay, now before we go over to multidimensional scaling, this is just a rehash of what we have done before. This is eigen decomposition or spectral decomposition in black, and the green, that's singular value decomposition. Eigen decomposition is, well, you know, for any square matrix A, it will be V lambda V inverse, but that becomes V lambda V transpose when we are dealing with symmetric matrices. Obviously, A has to be a square matrix for it to have eigenvalues and eigenvectors. Okay, so this is eigen decomposition. And from this, we get this theorem. A can be represented as a linear combination of rank 1 matrices Vi, Vi transpose, and the scalar is, the weight is lambda I, correct? And lambdas, how are they sorted? Lambda 1 has the highest numerical value, then lambda 2, then lambda 3. Of course, they could be negative 2, right? Unless this is positive semi-definite, lambdas could also be negative. So this is the general form of how you represent a square symmetric matrix as a sum of rank 1 matrices. And the lambdas are in decreasing order. Now, singular value decomposition, SVD, is a more generalized version of that, correct? So A can be applied to any matrix. You can do the singular value decomposition. It looks very similar to eigen decomposition, except we have, this is lambda is a diagonal matrix of all eigenvalues, and here sigma is also a diagonal matrix of all singular values. The difference is here the lambdas could be positive, negative, and if this is not a symmetric matrix, it could be complex quantities too. But here, singular values are always positive or non-negative. They could be 0, but they can never be negative. Okay, and we saw the proof of that too. Now, here is A, and A you can decompose just like you can decompose square symmetric A in this form using the Vi transpose as eigenvector transpose. Here you can express any arbitrary A as a summation of sigma I, which is a scalar, Vi transpose. So this Ui's are the columns of this matrix U, and Vi transpose are the rows of this matrix V transpose. Correct? And so Vi transpose is a matrix of the same dimensions as this, and so we are using this summation of rank 1 matrices to give us A. Now, sigma i's are also arranged in decreasing order. So sigma 1 is the highest, and they're all positive. We don't have to worry about taking the absolute values. So sigma 1 is the highest, then sigma 2, then sigma 3, and so on, right? Okay, and now how do you approximate A? By dropping the smallest sigma i's, right? And taking only the largest ones. Let's say we want rank 10 approximation, then we take the first 10 terms of this. Sigma 1, sigma 2, sigma 3, sigma 4 until sigma 10. and then sigma 11 and all, we just drop. They're numerically smaller than sigma 1, sigma 2, sigma 3, right? Okay, so this is how we approximate a matrix A, a low rank approximation of the matrix A. Now you can do exactly the same thing with this one, because numerically lambda 1 is higher than lambda 2, which is higher than lambda 3, which is higher than lambda 4, and so forth. Correct? Although they could be negative, or in the general case, well, we are looking at a square symmetric here. Okay. And so although this can in theory be complex quantities, but since we are looking at square symmetric A, so lambda i's are all real. Correct? Since lambda i's are real, so we only have to look at whether they're negatives or positives, and so we arrange them according to the absolute values. So if I want to approximate A, what should I do? Let's say I want rank 5 approximation. What should I do? I should take the numerically the highest 5, correct? That is the first 5 terms, if I want to use a rank 5 approximation. Where did we use this? In image compression, right? Okay, and today we're going to use this one. And another thing, when is lambda I always, well, we are dealing with a symmetric matrix. Suppose A is a symmetric matrix. Under what circumstances will lambda I be greater than 0, strictly greater than 0? Anyone? Exactly, when A is positive definite, strictly greater than 0. The eigenvalues will be strictly greater than 0. But if A is positive semi-definite, then it will be greater than or equal to 0. Correct? Okay. Now, so this is all we need to know. And there's one more thing. Well, the other one, maybe we can, actually what we'll need is only this time. Because we will be using the Gram matrix, G, something that I will explain. And the Gram matrix happens to be symmetric, and it also happens to be positive definite, strictly positive definite. So for the Gram matrix, these lambda i's are strictly greater than 0 because G is positive definite. This will be our G. Actually, this will be centered G, and I'll explain. Okay? Now, another point, this is the vector 1. It's a vector of all ones. By default, every vector is a column vector. So 1, 1 transpose is equal to, let's take a 3 by 1 vector 1. 1, 1, 1 times 1, 1, 1. What does it give us? If you do the multiplication, it will give us a vector of all ones. Okay? That's what we need to remember here. Okay, so now, time to fall asleep. Back to multidimensional scaling. Okay, so data samples, we are looking at a data science application. So we have a large number of data samples. Each point is a sample, which could be, let's say we have the United States, all the cities of the United States. The x coordinate and the y coordinate, or the latitude and the longitude, as an example. So these are the data points, and each sample index will be within parentheses because I'm reserving the subscript for dimension, okay, for rows and columns and stuff like that. So sample points will be indexed like this, and n equals 1, 2, 3 until uppercase n. So we have uppercase n number of samples. And each data point is a d by 1 vector. If we are looking at coordinates of cities in the United States. Each city is a sample, and D is 2 because we have two coordinates. And so this is the data matrix. Uppercase bold X is a data matrix. What I do is each data point is a column vector of D dimensions. I transpose that so that I get a row vector, and I take all the sample points together like this. This becomes my N by D matrix. This is the data matrix. The rows of the data matrix are the sample points. Agreed? And the mean of the sample points is 1 over n summation of xn. Correct? N is sample index, so it goes from 1 through uppercase n. And this will be a d-dimensional vector. If we are looking at the cities in the United States, then X hat will be somewhere in Kansas, maybe if we ignore Alaska and Hawaii. Okay, so this is our data matrix. And since we have n samples and each sample is a row vector, so we have n number of rows. And since each sample point is d dimensions, this X is a n by d matrix. Which do you expect to be higher, D or n? Hint, big data. N will be higher, right? Okay. But it also depends on the application. Sometimes you have very high dimensional data when we are doing genetics, bioinformatics, for instance. So each DNA sample will be it'll yield after some pre-processing, it'll yield a very high dimensional vector. But we won't have that many number of samples because it's hard to get individual DNA samples, isolate them, and blah, 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 I don't know. Okay, so when we say big data, it's not necessarily that we are looking at n being high, number of samples being high. Number of samples could be low, but D could also be very high, mind you. Okay, it's very high dimensional data. Okay, then we define the Gram matrix. The Gram matrix is G is defined as X times X transpose. This is X, this is X transpose. Each row of X is a sample point that's transposed. So the nth row is X transpose M, the nth sample point. And this is d-dimensional, correct? Now here, if we take the column n, that will give us xn, the nth sample point, correct? And how do we do matrix multiplication? We take, to get an individual element here in the product, we take rows of the first matrix and columns of the second matrix, correct? Here, if I take the mth row and the nth column, then I'll get my element mn in the product with this G. G equals X transpose. So, from here you can see that at the mth row and nth column, the corresponding element of this matrix G is X transpose N X N, which is the inner product of the mth sample and the nth sample. Okay? And the Gram matrix is roughly a measure of similarity. What's the expected value of the gram matrix. If these are random vectors, if any of you have done undergraduate probability theory or any course in random variables, noise and all in communications, then what if x and each x is a random variable, then what is this expected value of G, the correlation matrix? Okay. So now what we learned right now from this is GMN. This is the notation, right? Uppercase G is for a matrix, and lowercase bold g would be for any vector, and scalar would be lowercase italics, and so GMN is this element here, mth row and nth column of my matrix G, and that, as we just saw graphically, is equal to X transpose M Xn. Okay? So once again, we have the data points. Now what I'm going to do now is the data points. Okay. Let's say we are looking at the US, and the cities are the horizontal and vertical coordinates. We are, all 40 contiguous states are in the northern hemisphere, right? So the vertical coordinates would be, the longitudes would be all positives. And we are in the western hemisphere, right? So all the horizontal coordinates, the latitudes will also be, I misspoke. So latitudes would be all positive because we are in the northern hemisphere, and since we are in the western hemisphere, the longitudes will also be all positive, right? So what centering does is it'll shift the US to maybe somewhere in Africa, right below England, so that Kansas will be right at the equator and with 0 longitude. Okay. So that's called data centering. And I actually have a small example, so it'll be clearer. So how do we center the data? If we take each individual sample, how do we center the data? We simply subtract x hat from it. And that gives us the centered xn. So this is the raw sample, xn. X bar n is the corresponding centered sample once we have removed the average. What will be the average of all x bars if we have removed x hat from it? What is x hat? The average of all xn's, right? Now if I remove this, what will be the average of this? X bars, if I take all sample points, center them individually, and then compute the average, what will I get? The average will be 0, right? If you take the US and then we move it to that place that I told you, somewhere in Africa, where Kansas is right below England, so right below Greenwich. So the average of all horizontal and vertical coordinates would be zeros. So centering of data is done so that the average is all 0. And this is how you do centering. X bar, so this is each individual sample xn. So the data matrix you can sample using only one expression like this, which is good news for you because you can translate it to only a single command in MATLAB. X bar is equal to x minus 1 over n, 1 transpose x. And I'll have an illustration of how this works. So this is the centered data matrix. Okay, and how do I get this? The rows of this are centered transposes of the raw samples. You center the raw samples, take the transpose, and then arrange them together, so you get x bar, uppercase x bar. That will be the centered data matrix. Now, the expression is x minus 1 over n, 1, 1 transpose x. You see x and x here. So I take x outside. I define H equals I minus 1 over n, 1, 1 transpose. This is the centering matrix, H. Okay. H is defined by this. And you can see that H transpose is H. So let me write it down because this is an important expression. I'll write it down here. I'll write it down. Maybe I'll just erase this. I'll write down all the important expressions because there are 5, 6 of them and you might not be able to keep track of them. So H is the centering matrix is equal to identity matrix minus 1 vector transpose and 1 over n. What is n? The number of sample points. What is the size of H? N by n. Okay, so this is my H, and x bar is equal to H of H times x. So H times, I should have written it down, so x bar equals H times x. I hope it's visible. It's not visible there, but anyway, x bar, the centered data matrix is H times x. Okay, so these are two important expressions. That's why I wrote it here, and I didn't write it in the board, but H transpose is equal to H. If you take the transpose of this, what's the transpose of the identity matrix? Itself, right? I. The transpose of 1, 1 transpose is 1, 1 transpose. So H transpose is H. We really don't want the Gram matrix. What we are more interested in is the centered Gram matrix. Okay, now to give you the random variable example, if each sample point were a random vector, then G bar would be the covariance matrix. Not the raw correlation matrix, it will be the covariance matrix. In fact, the Gram matrix is a very broad term that includes the covariance matrix. It could include other matrices too, kernel matrices, and we use kernels all the time in machine learning. Okay, so centered Gram matrix we can obtain by taking the centered data matrix and doing the same operation. X bar transpose will give you the centered Gram matrix. So I take the transpose of the centered sample indexed M, so X transpose M, X bar transpose M here, and then from the nth column, what would be X bar transpose? It will be Xn bar. And similarly, if you take the product of this mth row and nth column, you get an element of G bar, which is equal to X bar transpose M X bar N, which is the inner product of the mth and nth samples, which after centering. Okay, and so I write it down here. Gmn is this expression. Same thing as this, and so I can get this expression here. G bar is equal to X transpose, or rather X bar transpose. Okay? This is the centered Gram matrix. And what's the dimension of this? G, it's a n by n matrix. What is uppercase N? The number of sample points. Because each row index m is a sample. And each column index n is also another sample. You can see this visually, right? This is the number of samples here I've assumed to be more than the dimension of each vector, of each sample. This is D. M by D, or excuse me, N by D, where an uppercase N times uppercase D is the size of this matrix, and this is D by N. Okay, next I define the squared distance matrix. This D, this is a slight misuse of notation. It's actually distance squared. I take pairwise distances between sample points, and then I get the distance matrix. So I take the mth sample and the nth sample. The square distance between them is dmn squared, and I get my square distance matrix by computing the square distances of every pair of samples. And this D will also be a n by n matrix, symmetric matrix. And what is the distance? The distance is obviously, if I take xm and xn, two sample points centered, then dmn squared is equal to, I'll not use L2 norm, I'll use this, xm minus xn transpose xm minus xn. And this is after the centering. So this bar is centering, and I use bars when I write something to distinguish between scalars and vectors. Okay, don't get confused. These are also vectors, and these are also centered samples. So whatever way you interpret the bars. Okay, so this is the squared distance, and I take the difference between xm and xn, the two sample points, and then I take the L2 norm, or difference transpose times difference, and I get dmn squared. And then distance squared, and this is I take pairwise all dmn's, and then I get my distance matrix D. Okay? Squared distance matrix, excuse me. So dmn square is, as I wrote here, xm minus xn transpose xm minus xn. Actually, I didn't use x bars here. I just took the raw data and before centering, and then I computed the distance matrix. Why is that? Before and after centering, the distances will not change. That's why. Now, I do this multiplication, what do I get? xm minus xn transpose xm minus xn. So I multiply them together, I'll get xm transpose xm plus xn transpose xn. I'm taking the two negatives here. That gives me another positive. xn transpose xn minus, I'll have an inner this xn and this xm, and then I'll have this xm and this xn, right? And both of them will give me negatives, and so if we do the math, you'll get negative 2 x transpose m xn. Okay? So this is dmn squared. What is each entry like this? X transpose m xn. Now here it's bar, that's why we get a centered Gram matrix, but without these bars here, before centering, what would you get? Here. Oops. What is this? X transpose m xn. It's the element in the mth row and nth column of the Gram matrix, correct? The raw Gram matrix, because I haven't used centered data here. So this is GMM, this is GNN, and negative 2, this is GMN. Therefore, we see that dmn squared equals GMN plus GNN negative 2 GMN. So if we have the Gram matrix, we will be able to compute the distance matrix. But our problem is the reverse. Okay. MDS is used when we have the square distance matrix or the distance matrix. You can square them element-wise. So once you have the distance matrix or the square distance matrix, then you do things. So our immediate goal is to express, not to find the square distances from the Gram matrix, but to find the Gram matrix from the square distance matrix. It's the opposite. Okay. So I'll do a little derivation, and in that derivation, this will be crucially important. This, using this expression here, I will do my derivation of how to get the Gram matrix from the square distance matrix. Okay, so now this is how we go about with MDS, multidimensional scaling. What we have is the square distance matrix, D. This is known. And our goal is to estimate, we actually don't have the sample points, we can estimate the sample point, the centered sample points. There's no way we can estimate what their averages were. So we just assume that the average of all samples was 0. And their relative locations, we can then estimate using MDS. So we assume that the sample points are centered. And then the first trick is to find the Gram matrix. We need to find X bar actually. Okay, there's no way we can find X, so we need to find X bar. And what's known as the square distances. And so this is how we do. The trick is first we find the centered Gram matrix G bar, which is X bar transpose. Correct? And we shall use the expression that I just showed you in the previous slide. And then we will show that this G bar equals negative half HDH. What is D? The square distance matrix. What is H? The centering matrix. I defined it here. Over here, I defined the centering matrix. And so this is the expression that I will derive. And then, so this is the first step from the square distance matrix. we get the centered gram matrix G bar, and then from the centered gram matrix we get the X bar. We estimate the X bar. Now, so this step is quite easy, right? This, but I'll prove it to you first. H you can compute. All you need to know is the N, the number of samples. That's already given to you, right? Identity matrix minus 1 over N, 1 transpose. Now, there was one little issue here. Why don't I get the... I thought I had the... I'll go back here. Oh, that's my problem. I uploaded it to slides instead of PowerPoint. I had a little example. Maybe we'll do the little example at the end, or do you want to look at it now? Let's look at it now. So I have 5 samples here. Each sample is 2-dimensional. So this is my data matrix. So 2, 3. So each row is a sample point, right? How many sample points do I have? 5. And what is D, the dimension of each sample point? 2. Correct? So this is a 5 by 2 N over D matrix. So 2, 3, then negative 3, 2, negative 3, 2, negative 2, 3, negative 2, 3, negative 1, and then negative 1, negative 2. Now if I add them up together and then divide it by N, 5, I get the average, right? So just add them all together. Let's do the first one. Plus 2, negative 3, negative 2, negative 1 gives us negative 5. Right? Negative 5 divided by 5, because we have 5 samples, we're doing the average, right, is negative 1. Likewise, you'll get plus 1. So X bar is negative 1 plus 1. This is the raw gram matrix, X transpose. 2 times 2, 4, plus 3 times 3 is 9, 4 plus 9 is 13. Then 2 times negative 3 plus 3 times 2 is 0. 2 times negative 2 is negative 4, 3 times 3 is 9, 9 minus 4 is 5, and so on. So this is my raw gram matrix. This is not the centered gram matrix, it's just the raw gram matrix. And the data matrix, okay, so this is how we do the centering here. X bar is identity matrix minus 1 over N. N is the number of samples, right? So minus 1 over 5 times 1 transpose of the data matrix, raw data matrix. What will happen if I multiply this identity matrix with the data matrix? I'll still get the data matrix here, right? And so let's do this. This will give us identity matrix times X will be X, negative 1 over 5 of this. Okay? And this gives us, this is X bar. Now, after you do this, what's the sample average? Well, after centering, what's the sample average? 0, correct? Remember the US analogy. I'm moving the United States to somewhere in Africa below England so that the average will be, which is around Kansas, that will be exactly latitude 0, longitude 0. So if you take the average coordinates of all cities in the United States, you'll get a big 0. You can verify that here. Take the average of what's the sum of the x coordinates? And we have x coordinates and y coordinates, right, in 2 dimensions. So don't confuse it with this x here. So x coordinates, if you just add them up together, what do you get? 3, yeah, you're getting 0 here. And here again, you're getting 0. So the average of this will be 0. So this is the centered Gram matrix. We saw how to compute the raw Gram matrix. If you do the exact same thing with x bar, then this is x bar. You would get the centered Gram matrix, right? So square distance matrix. G bar is this. And so this is the distance matrix. What's the distance, pairwise distance matrix? So here the distance of a sample point to itself is 0, right? So the diagonal elements here are all zeros. The off-diagonal elements. What's the distance between, so we're looking at row 1, column 2. What's the distance between sample point 1 and sample point 2? Difference between this is 5. 5 square is 25. What's the difference between this? 2 and 1 is 1. 1 square is 1. 25 plus 1 is 26. Right? Between 1 and 3, what's the difference? Plus 3 minus of minus 1 is 4. So 4 square is 16. Difference between plus 2 and plus 2 is 0. 16. Between this and this, 3 minus 0 is 3. 3 square is 9. Plus 2 and minus 2, difference is 4. 4 square is 16. So 9 plus 16 gives us 25. And between the first and the last sample, 3 and 0, difference is 3. 3 square is 9. 2 and negative 3, difference is 5. Plus or minus 5. 5 square is 25. So 9 plus 25 is 34. You get the pairwise square distance matrix. This is the square distance matrix. And these are the steps of MDS. Okay? We will show that the centered Gram matrix is negative half HDH. So D is dmn squared, and we just saw this expression here, right? For dmn squared in terms of the elements of the Gram matrix. Now I define this lowercase g vector, diag g. Okay, so this is, look at the diagonal elements of G. G11, G22 until GNN. Okay. Now in the Gram matrix, these actually will be relatively high, right? Because look at I didn't compute this, the centered Gram matrix, but you can always fill it in. Okay, so where's the Gram matrix? One thing you'll note in the Gram matrix is the diagonal elements are relatively high. Not always the case, because this is plus 2 and this is plus 3. This is because -1 is a relatively small vector. The length of this vector is relatively small, and these are bigger vectors, right? That's why it's not that you'll get the highest elements here, but you'll get usually you'll see that the elements are higher in the diagonal. If you have only normalized samples, so if I were to divide this by what's the length of this? 9 plus, so this is square root of 13. I divide it by 1 over square root of 13. This I do 1 over square root of 13, 1 over square root of 13, and this 1 over square root of 2, and 1 over square root of 5. Then I would get normalized data, and with normalized samples like this, I would have gotten all higher values here. It would have been cosine thetas. And all of these actually would have been 1s, and all of these cosine thetas would have been between -1 and 1. Okay, but I didn't normalize the vectors. But still, these are always positive, the diagonal elements, and they're relatively big compared to the other numbers you see in the graph matrix. So what I do is here, I take these which are all positive, and these are relatively large. The diagonal elements, G11 until GNN, and then, see, this is a notation of what I'm doing here is I'm taking the diagonal elements and then I'm forming a column vector out of those. So G11, G22 until GNN will be this vector G. Okay? Next, you saw this, right? This is how I defined my vector G. This is what I'll prove first. What I need to prove is, this is what I'm ultimately trying to prove. The first step of the proof is this. G1 transpose plus 1 G transpose negative 2G is equal to the squared distance matrix. Okay, and this lowercase g vector is a vector of all the diagonal elements. What is 1? 1 is a vector of all ones, correct? 1 transpose is a row vector of all ones. If I do G times, this is G, times 1 transpose, what will I get? The same G will be repeated so many times. 1 transpose is a row vector of all ones. 1, 1, 1, 1, 1, 1. Right? So G1 transpose gives us this G1. So the first row here is all G11s. Second row here is all G2s and so on. The nth, the last row is GNN. Along the columns, that's another way to look at it, G11 through GNN. This vector G. This vector G again, so this vector G is repeating n number of times. So this is G times 1 transpose. Now we take the transpose of that. So what's G times 1 transpose? What's the transpose of that? 1 transpose, transposed is 1, correct? I have to, when I take the transposition, I have to do the multiplication in the reverse direction. So 1 transpose transpose is 1. 1 times, what's the transpose of G? G transpose. So that's 1 G transpose. 1 G transpose is, so the columns become rows, right? So each of these is this G transpose. G transpose, G transpose, G transpose until G transpose. Repeated n number of times. This time it's row-wise. Are we good until this point? So G1 transpose plus 1G transpose, negative 2G equals, next that's what we will show is equal to D, square distance matrix. This is my G1 transpose. Each column is my vector G, which comprises of the diagonal elements of the gram matrix, of course. So G1 until G11 until GNN, again G11 until GNN, repeated n times. And this is its transpose. G11, GNN until G uppercase N, again. So the rows of this second matrix are the same. The columns of the first matrix are the same. Now let's examine what do we have in row M. And here I have negative 2. This is my G. G11 until G1N. This is the actual gram matrix. GN1 until GNN. Now observe the red. We are looking at row M of all three matrices. In the first matrix, it's all G, M, M. M as in Missouri. For the second matrix, it's G11 until GNN. G11 and G22, 33, 44 until GNN. Right? That's at the mth row. And here I have negative 2. Here I have GM1, GM2 and GMN until GM uppercase N. Correct? Now let's look at column N. When we are doing this, these are all additions and subtractions, right? Addition and subtraction here. So let's see what's going to happen to the mth row and nth column. This entry element here is GMM. What's this element here? Again, I take the nth column, so I get my element in row M, column N, that will be GNN. Right? What's row M and column N here? Negative 2 GMN. Right? So what am I getting here? So this, what do I get here? When I do this, when I add them up, entry MN will be GMM plus GNN negative 2 GMN. Agreed? Which is what? Dmn squared, because we just saw this earlier. Agreed? So this is Dmn squared. So we saw that each element is giving us the right element at the correct position, row M, column N of the square distance matrix. Therefore, this is G1 transpose, this is 1G transpose, this is negative 2 uppercase G. I get this expression. Okay, so this expression I just proved. Now, I don't have to write it down because it's in the next slide. Now what I'll do is we will use this expression to prove the main thing that I want to prove. So we saw this, and this is my definition of H. What we will prove is the centered gram matrix is negative half HDH. Okay? Then, given the data matrix, you can obtain the centered gram matrix. That's the first step of our MDS. Okay. What I'll do is, let's look at H1G transpose. This is G1 transpose, this is H1G transpose. H is this. I plug in the value of H, then 1 G transpose. Then I open the bracket, this is what I get. This is identity matrix, right? So I get 1 G transpose, negative 1 over N, 1 transpose, 1 G transpose. What is 1 transpose 1? We know what's 1 transpose, right? That's a matrix of all ones. What is what is 1 transpose 1? We'll take a 3 by 3 example. So 1 transpose is 1, 1, 1, and 1 is, what do I get? 3, right? That's because I have 3 ones here. If I have n ones, then I'll get n here. Okay, I know the dimensions, 3 is the dimensionality of this, but I'm taking the number of dimensions here to be equal to the number of sample points because I have to match the matrix sizes. So if the number of samples is large, then all these matrices are large. Okay, so H1G transpose equals this. I just came to this step. This 1 transpose 1 is 1 over n, correct? And from the associative property, I can do this multiplication first, 1 transpose 1, and I replace it with n. So I get in the second term, the first term is still 1G transpose, the negative 1 over n, 1 n G transpose. N and n will cancel out. Agreed? So I get, this gives me 1 G transpose as the second term. The first term is 1 G transpose. What do I get? A matrix of all zeros. Correct? Okay, so H1G transpose is all zeros. So this is what I just got. What if I do the transpose of this? I'll get G1 transpose H, correct? Because I just did the transpose, and so I'll still get a 0, a square matrix of all zeros. Large square matrix equal to n by n matrix of all zeros. Are you guys with me? Okay. So these are both zeros. So this I write here. So these are the expressions that I have. G1 transpose plus 1 G transpose negative 2G equals D. And here I just saw that G1 transpose H is 0, H1G transpose is also 0. So now let's prove this, the main proof, the last stage of our proof. Negative half HDH. We just saw that this square distance matrix is equal to this. I plug in this value here. I open the brackets. So negative half H G1 transpose uppercase H negative half H 1G transpose H, and then negative half here and negative 2 here. So plus 1 plus HGH, HGH. The first term is 0. Second term is 0. So what are you left with? HGH. Okay. HGH, where G is the Gram matrix. What are we looking for? The centered Gram matrix. We saw that negative half HDH is equal to the Gram HGH, where G is the Gram matrix. What do we have to show now? That HGH is G bar. But G is, by definition, XX transpose, right? That's how we get G. I gave you that example too. And H is a symmetric matrix. So this is equal to HX is, what is HX? The centered data matrix, right? H is, that's why H is called the centering matrix, because if you pre-multiply it with the data matrix, you get the centered data matrix. And since this is H is symmetric, so this is the same thing as H transpose. X transpose H transpose is transpose of HX, which is X bar transpose. What is this? X bar transpose. G bar. Just like G is XX transpose, G bar is X bar transpose. So we got this. G bar is negative half HDH. So this is the first step, and we just saw how to do the first step. Finding the centered Gram matrix. Now, the next step is to do the spectral decomposition of G bar, centered Gram matrix. G bar will be a symmetric matrix. And we should, at the end, I'll show it to you. G bar will be a symmetric matrix. And so its spectral decomposition will be of this form. And G will be the centered Gram matrix. Actually, any Gram matrix is always positive definite. Okay, just remember this at the back of your head, not for this course, but in the long run. So this is always a positive definite matrix, the Gram matrix. So what will happen to lambda? Lambda, all the eigenvalues, right? It's a it's a diagonal matrix of all eigenvalues. All the eigenvalues would be strictly positive. Whence X bar, this is an estimate actually, is equal to V lambda half, square root of lambda. If this is X bar, then what is X bar transpose? So if I get my let's have so G is equal to V lambda V transpose, and this lambda is a diagonal matrix of the eigenvalues, correct? And then what I'm doing is we know that G bar actually is equal to X transpose, right? Now, if I take, what I'm claiming is that X bar is equal to V times square root of lambda. How do I do the square root of lambda? Since it's a diagonal matrix, all I have to do is take the square root of all the elements, right, of the diagonal. And they're all positives. Therefore, the square roots will not turn out to be imaginary. You take the positive square roots. You can actually take the negative square roots if you like. So this is my, so anyway, so this is my claim. So from here, let's see, if this is this, then I replace this here, what do I get? XX transpose is equal to G, XX transpose is equal to V square root of lambda, V then square root of lambda, and then what's the transpose of this? Same thing, because it's a diagonal matrix. The transpose of a diagonal matrix is itself square root of lambda times V transpose. Right? And so if this is the spectral decomposition of G, then this is my X, because if I multiply these two, the diagonal matrices, right? So it's very easy, I'll get lambda. V and V transpose at either end. So this is what I do. I take the spectral decomposition. So step one is find the centered Gram matrix, and then I do the spectral decomposition of the centered Gram matrix. Correct? And then that will give me this. The X bar, the centered sample points will be V square root of lambda. And that's my objective of MDS. Okay? Now, I said that this was positive definite. Okay, now let's look at the Gram matrix again. Actually, let's look at the Gram matrix, note on the Gram matrix. This is, I'm using by default the centered Gram matrix. So G bar is XX transpose. So G bar transpose is X bar transpose, which is XX transpose, which shows that G is symmetric. G bar is symmetric. So it has real eigenvalues. Now, why is it positive definite? Take any vector v. Now, this is not an eigenvector. Any vector v. I should have maybe, I didn't want you guys to get confused with x, which means sample point. Now, I'm taking any arbitrary vector. So, v transpose gv is this. V transpose xx transpose v, which is now I club v transpose x together. That's x transpose v transpose, x transpose v, which is L2 norm of x transpose v squared. And since it is a square, it's always greater than or equal to 0. So G is symmetric positive definite. Okay, because it's possible to get all zeros. So when is it positive semi-definite and when is it positive definite? Let's go back and look at the definition. Just the Gram matrix, forget the centering, it's the same thing, centered Gram matrix or the regular Gram matrix. Okay, this is the Gram matrix. XX transpose. If the number of, if the dimensionality of each sample point is low, then what will happen? I have, like in my example, I have 5 samples, right? Where is my, I have 5 samples, but the dimensionality is only 2 dimensional. Okay. Then what's the situation here? 5 by 2 matrix, 2 by 5 matrix, I get this. What will be the rank of this? It'll be only 2. You have to take the smaller one, right? So the rank of this matrix will be only 2, so it will have how many how many non-zero eigenvectors will it have, eigenvalues, will it have? Number of non-zero eigenvalues is equal to the rank of the matrix, right? So in this case, where the number of dimensions is low, what will happen? This will be a low rank matrix. And then when we do the spectral decomposition, what will happen to the spectral decomposition? When we do the spectral decomposition, lambda 1, lambda 2 will be some values, positive values, but what about lambda 3, lambda 4, and lambda 5? The smaller eigenvalues, they will be zeros, right? They will be zeros. So if we have low dimensions, if the number of sample points is large and the number of dimensions is low, D number of dimensions is less than number of sample points, then what will happen? You don't have to do the spectral decomposition, find out all the lambdas, only a few. Because the Gram matrix is positive, semi-definite. Now on the other hand, let's look at the other situation. Suppose the dimensions were high. We're looking at 1,000 dimensions data. Then what would happen? The Gram matrix would be high dimensional. It will be positive definite, not positive semi-definite. It will be positive definite because it's full rank. Okay, so now if we have high dimensions, D is more than number of samples, then what we can do is, this is the last point that I'll make, go all the way to the end. So then an important application of MDS is called dimension reduction. So this is the spectral decomposition. Okay, so this is n by n, number of sample points by number of sample points. And if I want only 2 dimensions, what do? I just take, remember, approximate, low rank approximation. So this is, eigenvalues are non-negative and of decreasing order. And now I take the square root of that, I get x bar. This is an estimate of x bar, by the way, because I'm losing information already. Because number of dimensions, D is more than n number of samples. So this is x bar. Then what I do is smallest eigenvalues, I'll drop, I get the low rank approximation. That gives me low rank, or that will give me reduced dimensional data. What are the coordinates in my reduced dimensions? The eigenvectors. So this is the low dimensional data. And I can drop this part of the matrix V. These are the eigenvectors, right? Corresponding to small valued eigenvalues. So this is for drop the lowest eigenvalues and I get this. This is basically a reduced rank approximation of G bar. Right? And so from that I can retrieve my x bar. What does MDS do? You're starting off with the square distance matrix. So in the low dimension approximation, it will try to arrange the coordinates in such a manner that the distances are preserved, pairwise distances. Isn't that great? End. Any questions? Do you guys have any questions or? Okay, didn't see anything on TV. I just hope that we recorded everything.